Okay, you guys can see the screen, right?
Yes.
Yeah, okay. So, I mean, the past 3 weeks, if you will, was basically, laying down the foundation for actually what we are going to learn today, right? Because convolution neural networks, and then later on we'll see like recurrent neural networks or transformers, but convolution neural networks are the ones which really propelled the whole, fields of, AI or especially deep learning, right? The reason most of these applications exist today are all because of convolution networks. And you will see, there's a reason why, just the multi-layer perceptron doesn't scale. And in fact, in the 90s, when, multi-layer perceptrons were kind of, being used, and it was one of the tools, including SVM and decision trees and stuff, but it never, was really good because it suffered from this overfitting, because you have so many parameters. The number of parameters scaled very quickly, and very quickly it overfit. And you'll be surprised it took a long time for people, like from 70s till 90s to figure out a way to reduce the number of parameters. And that's what we'll study today. But just to give go a little bit higher level, let's look at this one nice example. I'm sure you have seen this form of apps or examples, but I just wanted to show you that these are like 5 like really famous paintings, right? And now you have all these apps where you can take a known, take an image or take a photograph that you have taken, provide this particular art by your favorite artist, and this model or this technique or this tool can apply that theme, right? Because now it is very hard to quantify what does a style mean, like what does a theme mean, right? But if someone were to look at these images, they will kind of like, oh yeah, it does look like this image has a very similar style as this, right? Now you might say, oh, does the style always means color? Probably not. I could just change the color of this image right now, and it will still look same style, right? Even though the color profile, the color palette might not match, because there's something called as texture, there's some lines and all this stuff. So for a long time, even though people wanted to, it was hard to do this kind of thing because it's ill-defined problem, right? Because style is something that's so hard to quantify. But however, it turns out with the CNNs, again, it's just one of the properties. It's not that somebody actually went out to inject a style in CNNs, but when you train CNNs on images, it implicitly learns this style. Like we don't know what, but like all these bunch of numbers, if you put together and if you transfer these numbers to another set of images, I'll show you towards the end, it does look like this target transfer. So this is one of the cool examples. But there are other very practical examples. Just recently I was traveling, and all the signs were in Spanish, and I could use my phone and it does translation right away. Now remember, I'm not typing some text, I'm just giving the image, and from the image it is able to get the patterns, get the text, and then of course there might be other NLP model that does the translation, but it can overlay in a similar style. So to me it almost feels very natural to use the phone to look at these translations. Similarly, I'm sure you have seen these tools that convert black and white photos to colorful. Now you might say, how does it know what is the true color, right? Because this car could literally be blue or black. Who knows what the real color is? But here the idea is, colors are sensible, meaningful, and probable. In the sense, when someone were to look at these colorization outputs, they might think, oh, this is this is practical, this is realistic. It need not be accurate, but it just has to be realistic. And obviously Tesla, which exclusively uses cameras, relies a lot on computer vision and CNNs to be able to do the driving. I know this example is from a few years ago, but I think some of the newer Teslas have better capabilities. Of course, that doesn't mean it is there yet in terms of fully being autonomous, but CNNs have definitely made it possible. And I personally, worked at healthcare startups where CNNs are being used to analyze X-rays, analyze pathology, analyze your cells, biopsy, and everything. And no humans will be able to do the things that CNN can do. That is, analyze billions and trillions of images without by being very consistent. Like, it doesn't mean it's 100% accurate, but it is far too consistent compared to human beings. And just to show that how important this was, the first guy here, Jan LeCun, his contribution in the whole deep learning era is this convolution neural network, CNNs, because CNNs, if you see, they are just a special case of what we have learned, but that special case being so useful that it was worthy of Turing Award, which is equivalent to Nobel Prize in computer science. And obviously Jeffrey Hinton is credited for the backpropagation, and Yusuf Binji is credited for general understanding of deep learning and how it works. Okay, now let's get into this convolution neural network. So before we understand CNNs, we need to understand this process of convolution. And again, if you're from the image processing background or signal processing background, or even from applied maths background, it's a very trivial process. But if not, it might seem a little bit, out of the usual norms. Idea is, you have this input, it can be 1D, 2D, 3D, but for all our purposes, we will just assume 2D because, mostly we'll be dealing with images. So, you have this image, which is 2D, and now you consider another small square image, which is called as kernel. So in this case, the kernel is 3 by 3, and, kernel typically has, some values. In this case, just for simplicity, it's all binary values. So the kernel values are the ones that are, in the red in the bottom right. So once you superimpose so a kernel is 3 by 3, right? So once you superimpose this 3 by 3 kernel on top of the 3 by 3 of the image, you do the pointwise multiplication of the values in the kernel, that is the, the red values, and the values of the image. So here, one is multiplied by, is there a way to actually pause this? Let me see, there must be some way to pause this, right?
It looks like a mask almost, right? As the window's sliding, it looks like you're only selecting one, you're multiplying 1 by 1, 0 by 0, right?
Yeah. So it's okay. Let me actually use this tool. There is a reason I have this link, because here now we can see this interactively, right? So first of all, let's look at what an image looks like, to your computer, right? Because to us, our brains are really good at finding patterns. So when we see this, we see a face. But in the computer, each of the pixel is represented by a number, and if it's a grayscale, it's a single number, and typically this number is only 8-bit, that is 0 to 255. And the reason is because we don't really need more granular difference, because we aren't able to tell the difference. Now, of course, that depends on the like how large the image is. If this image were, like, for example, small like this here, changing the depth of each of the pixels color wouldn't make any difference for us, but for computer, of course. So therefore, these are 8-bit numbers. Now, let's say our filter is, let's take a simpler filter like this, right? So here, the filter values are this. So what we will do is, let's look at this particular center here. I hope you guys can see the red square on the image on the left.
Yeah,
right?
they're showing up.
Exactly, perfect. So on the red square, this is where my kernel is overlaid, and the values in the center. Oops, now I can't go to center without. So the values you see in the center, like, these are the actual pixel values, and now each of the pixel is multiplied to its corresponding value in the kernel, right? And if you see here, our kernel, the top left value is 0.0625. So you take the top left pixel value, that is 178, multiply by this kernel. Then take the second pixel, multiply by its corresponding value in the kernel. And remember, the kernel value could be anything, right? If our, and all these names have some meaning, but we'll come to it. But it could also be something like this. So kernel values are all 0, except for the center pixel, which has value of 1. So let's go back to this one. Here, what you can see is, if center is 1, this, like, that is, and everything is 0. What you're essentially doing is you are simply replacing that center pixel, right? Because once you have multiplied these things, and now you add them all, and this 3 by 3, or these 9 values, becomes one single value, and that value is replaced to that center pixel, right? So here, the center pixel would be like on the center of the right eye, right? So you can see here, I'm using the neighboring pixel values to add to the center values. right? And essentially, if you think about what does a blurring mean, blurring the edges, blurring the lines, it means you dilute the value. That is, you take the neighboring values. So this is why this kind of filter, where you are essentially adding a little bit of its neighbors to its own value. So you are first of all, making its own value to be 1/4, right? So its value is only a fraction of what's of its original value, but the other 3/4 comes from its neighbor. So when you do this, you basically get a blurred output. Similarly, so what would it be like if I were to, say do, let's see, so bill is for, let's do this outline right now. Let's see here what this does. So here, the center one, I'm taking 8 times and I'm subtracting all the neighbors, right? So essentially what it does is, if you have a sharp edge where, if my neighboring pixels were 0, this will be multiplied by 0, right? So say I have, all my top left neighbor values to be 0, right? Then what happens? This value is slightly higher if I had all the neighboring values. Why don't you guys do this, right? If you have a paper and pen, try to see, try to make an image here. Let me see if I can annotate. Let's see, let's do this. So say if I have an image which is which has the values like this: 1, 1, 1, 0, 0, 0, and let's say 0. So this is your example 1, and in your example 2, move this 1, 1, 1 to the bottom row and zeros, and then make the first 2 rows zeros. If you do that, so if that is your input and this is your kernel, what do you think will be the output? And because I want to get you, because I want you guys to get a sense of what is like, what do these numbers actually capture? Like why is it this significant that you have ones in the middle, zeros everywhere? What is it trying to find? So I'll give you a few minutes, give it a try. And if not, I will give you some more intuitions regarding what is going on here.
Are we doing piecewise multiplication and then adding all elements?
Correct, exactly. So 0 is multiplied to -1. So all the top row is 0, all the bottom row is 0. This will become 1 multiplied to -1. So this is -1. This is 1 multiplied to 8. So this is 8. This is -1. So essentially this becomes 6, right? So this becomes 6. Now let's say the, so right now we are doing it for this pixel, right? So for this pixel, the value is replaced by 6. What about this pixel? So this is basically 0 multiplied by 8. So that is 0. And all, so let's say this is here 0, this is 0, this is 0. So it only has these 3 neighbors. And these 3 neighbors are multiplied by this -3. So you basically get -3, right? Similarly, we can say this one, the one on the left, this one will also become like -3. Imagine if there is a 1 here also, right? And there's a 0 here, right? So you get -3, -3, 6, 6, right? So you can see here now, this is starting to find things where you have edges, right? Because if you have, so for example, if these were all ones, right, then you will have some all the let's say this all were ones here. So this will probably you'll have some higher values, and let me say you'll have some positive value here. Oops, some positive value here, some positive value here, or if I were to simply treat this as, let's say binary, let's say that is, whether the value is greater than 0 or less than 0, this will become like 1, 1, 1, 0, 0, 0. And remember, even if this were not 1, 0 here, for SimCity, if you're 0 0.2, 0 0.9, 0 0.2, 0 0.1, something like this. So the idea is, if you have a concept and if you have an image that is that is going, that is changing the contrast, this particular kind of filter will capture that. And the reason I'm saying this is because this is going to be important, because for a long time, there's a whole, first of all, the whole convolution to do image processing is not new. If you open your Photoshop or any of your app, even your camera in the phone will allow you to do simple things like, sharpen the edges, or, apply some blur, or apply some, this emboss, where basically, it's the reverse of finding an edge. And then you can do sharpening, all these things. There are these tools that will do this, right? But for a long time, what people did was this kernel value, right? And so this is called as kernel, right? So we're convolving with the kernel. Right? So the process of convolving means taking a kernel, doing this block, then moving 1 pixel on the left, doing the whole row, then going 1 pixel down, then doing this whole row, then going 1 pixel down, doing the whole row, and then doing all of this, and then getting the output image. This process as convoluting an image with the kernel. This is a old thing that used to be done for so many image processing techniques. The magic of deep learning with the power comes is you don't need to find these. It's like you don't need to know the right kernel values. You can start from anywhere, and basically, as long as you know what you want, that is, you have the ground truth or the output image, you can tell the model to figure out the kernel values. And in the end, the whole convolutional network is just a glorified way of doing, find these kernels. However, later on, you will see there is some complexities around that, but essentially the process is that. Now, you don't have to implement, this convolution process, Keras already has, keras.nm.com 2D will do it. But, if you guys are really good at programming, I would encourage you to just write down the whole convolution once, because you'll be surprised how many for loops it takes to basically convolve a kernel to an image and get this out. And the other thing that will be really key in your practical thing is figuring out the output shape, right? Because here you will see, or suddenly this, because in the previous example where I was showing you, it was big enough that you didn't notice. But if you see the output image here is smaller than the input image. Why? Because once you have reached, so once I moved here, now you can only have this row be the center. You can't have this row to be the center, because there is no, there's no final out, final right side column here for me to convolve completely. So question is, and how do we handle that cases, right? Because I need at least 9 values on the image to convolve for a given point. Similarly on the bottom side. So this is where the idea of valid convolution or convolution with padding comes in. What you are seeing here is called as a valid convolution. That is, at the edges, you just don't have the remaining one. So what will be the output size? That depends on the size of the kernel, right? So here in this case, my kernel was 3 by 3. What if my kernel was 5 by 5, right? Then I will have my kernel on top of this, 1, 2, 3. So whole thing is 5 by 5. So I will have the kernel here, and output size literally will be 1 pixel, right? I won't be able to move at all. And what if my kernel is 4 by 4? Now, there's a reason not to use even sized kernels, but say if I had a kernel 4 by 4, once I reach here, I won't be able to go do more. So I will lose 2 columns here, 2 rows here. So the output will be -2. So you can see here, output is always, it is always 1 less than the size, or 2 less than the size of the kernel, right? And also there's a formula, but you need to know why this happens. And all this time, I'm assuming that, once you have done the convolution process, you're moving it only by 1 pixel, and that's called as a stride. But sometimes you might just want to completely omit the, the alternate row. Say so after doing the first 3, I don't want to do the second 3. I want to do the third 3. So I'm skipping over this. So when you have this stride, the size of the output will be different. So there's a formula, also the formula, but you should know why that comes.
So
go ahead.
I think it's pretty clear on how this is working, but why? Why would we want to do this?
Absolutely. I will come to the why, and there is a good reason why we want to do it. Most importantly, when you look at it, so let's look at this image right now. This is a high, high density image, in the sense the number of pixels in this image is a lot more. Now let's look at literally, pixels that are neighbor to each other. Let me see, I think I can zoom my screen from here. One second, let me figure out how to zoom my screen. I thought I had. Zoom. Okay, so let's look at let's take that square box there, and take a similar size. What I'll do is I will really make it big so that you can see, right? So if you see that small part when I really zoomed out, now tell me, is there any different now in this case, actually the computer is doing some interpolation, so it's not really a true representation, but still what I'm trying to show you is the difference between the pixels that are, at position I and I+1 is going to be insignificant given very large images, right? If images are very small, probably that's all right. But if images are big, you could really not do every alternating pixel and not lose any information, because between pixel I and I+1, the values hardly change. So therefore, there is no new information. So basically, you downgrade your signal because the added value in there is a lot less. Now, question is about what is any downside? Downside is yes, right? Because it's all about compute cost. Like the more computation you have to do, ultimately, the longer you have to wait, and you would rather for the same amount of time be able to process more data. And these things are getting very expensive that, some, for small companies cannot always afford to, do some of the big computations. And today I'll show you later on how many parameters we're talking about. So in the end, it is mostly about saving computation. And there is also some idea of regularization, because in machine learning, just because you have more data points doesn't necessarily mean you have a better model. You need to have more data points that has more diversity. So just by adding another row of pixel that is very same color, you're not adding any diversity, but just you're adding more data. And that kind of thing actually leads to overfitting. So there is some form of regularization also if you do strided convolutions. Okay, now let's come to the intuition on how did we, so we understand the idea of convolution, right? We understand the idea of MLP, but how to put these things together, right? Where does this, like how does the convolution and MLP fit together? Because at the start I told you that convolutional neural networks are just a special case of multi-layer perceptron. That is whatever we know of this, 2-layer, 3-layer hidden neural network. Convolutional network is just a variant of that. So the idea here is you have this dense connection here, right? That is every input is connected to every output. What if not every input has to be connected to every neuron, right? So let's assume, let's think about 1, 2, 3, 4, these 4, points, these 4 pixels, right? Now, each of the kernel, we can assume that is trying to find something or trying to extract some information. Now, the information that you'll find between the pixels that are close by will be something similar, right? Probably it's possible that these 2 points, they both belong to the kitty. Yeah, in this case, it doesn't, but it could because they're close enough. But however, if 2 points are very, very far apart, unless it's a really, really big object that is taking up the whole image, it's kind of safe to say that whatever information you have at this point is different than whatever information you have at that point. Or, so when I say different, what if there is an object here and there is another copy of object here? Technically, yes, they are the same information, but the instance is different. They're part of different objects. So your kernel would want to be kind of independent. That is, look at this and look at the neighboring areas, but not everything, because idea is there is something local that you want to capture and not global. And intentionally I'm being vague here. I'm not telling you, that's capturing the texture, color, because there's this idea that these things happen at a multiple layer over time. But let's just imagine, let's just go back to the edge detector. Say my kernels are trying to find edges. So, there won't be an edge that will, that I will need to go from here to there and at the same step in order to know if there is an edge. If there's an edge, probably, for example, the edge is here, right? So here, by doing convolution, I won't be able to capture it. But if I'm convolving here, I only need to go a few pixels in the neighborhood in order to find the edge. I don't have to go from here to there. And that is why the idea is that not all of these hidden layers, not all these dense connections are necessary. It can be sparse. So by sparse, let's say like this, that the first few inputs are only connected to first few neurons, then the other inputs are connected to other neurons, and the other inputs are connected to other neurons. And now you can start to see how this is starting to look like a convolution where if I had a, and remember this is a 1D data. So if I had a 1D filter of of size 2, so basically then I have a filter of size 2, and the input of 2, I will convolve this to get one output, then move the filter. Now in this case, I have a stride of 2 also. So I go from this 2 input to this 2 input to this 2 input. And then, and then if you see there, the math of the convolution was same as this, same as what we know from MLP, right? That is the input multiplied by the kernel weight, and then, sum of all such connections, right? So here you will get this as the input. Now, in this case, when we're doing MLP, this was one weight, this was another weight, this was another weight, this was another weight, this was another weight. Here, what I'm saying is it's just the same W1 and 2, but first you convolve these two, then you convolve this two, so you convolve this two. So essentially, we went from how many? 1, 2, 3, 4, 5, 6, 1, 2, 3, 4. We went from 24 weights to just 2, right? And you'll see there's a huge reduction in number of parameters. Now, essentially, of course, it cannot be the case that these two networks are equally capable, equally powerful, right? But if your inputs are images where you have this idea of locality, that is, and objects are almost always contiguous, they are convex, they will be convex, but, they are in the, like one object isn't, like 10 pieces in 10 parts of the image, right? A single object is always contiguous. So all of this cat is, connected to all the, kind of all the pieces of the cat. And if you have this kind of notion, this kind of locality, and the idea that this cat could also come in this corner or in this corner, on this corner, and I would want it to mean the same thing. That is, regardless of where the cat is, it is still a cat. And this concept, and this is a very important concept, is called as a translation invariance, right? That is, so translation means movement. That is, wherever the object moves, my output should still be the same. So here, if I'm trying to find features of a cat, regardless of where the cat is, I need to find the same features if it is the same cat. It means, I want this whole thing to be invariant to translation. And so if I had this kernel W1, W2 that captured this cat, and if I were to convolve from top to the bottom, whatever the cat is, that cat would emerge, that feature would emerge, and it would not matter where the feature is as long as the feature emerges, right? So you can see how doing this convolution process, that is sliding the kernel, you are baking in the translation invariance. And then the other thing would be, how about the scale invariance? Regardless of the size of the cat, I would want it to still be the cat. Now, just by doing this, you don't get scale invariance, but you'll see how, there are other things that we add in, the convolutional networks that make it a scale invariant. And now, for example, if I were to flip this image left to right, probably, it's still the same cat. And this, so this kind of rotation of flip invariance, you don't always get it, but most of the features are very symmetrical. Most objects are symmetrical, and by implicitly you get this kind of scale invariance, flip invariance, because the data by design is symmetrical. Okay. So far, any questions? Because it's very important to get these mechanics right, because these are things that will always be true. Even if somebody were to design a new type of neural network or a new type of convolutional network, the whole process of convolution and idea of the kernels, whatever, will still be the same. However, the actual implementation might be different. Go ahead.
How about the hidden layer, the neuron, the top neuron? It's not getting any inputs, but it's still providing output for the.
So this one, right? This top one, right? So you can. So if you remember, last time we discussed the idea of bias, right? That is, in each of the layer, there's one unit that always has input of 1. right? Because idea of the bias is allows you to change the mean of where your activations are, and therefore you can treat this hidden unit as bias. But if you don't have biases, imagine this doesn't exist.
Yeah, it's like weights are equal 0, and they cancel out any x's.
Yeah. Okay, so so this is what I was saying, that this is same weights, you do the convolution. And so in this case, like I said, the size of the filter is 2 because you have 2 weights. Stride is 2 because I'm taking the first 2, then I'm taking third 2, then I'm taking fifth 2, right? But if I were to do this 2, then 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 the stride would be 1. Okay. So it's exactly so the way I said, right? The difference between stride 1 and stride 2 is this. Okay. Now, but this is still 1D, right? That is, your input is 1 dimension. And like I said, this whole idea of doing convolution only kind of makes sense if your data are images, or you have that in locality. Now, there are other 1D image data, so 1D data that where you would want to apply convolution, like your time series, or like some kind of a signal, some kind of a continuous variable from a like a measurement, or like climate, other stuff. But those are very rare because there are better techniques to apply there. So now let's look at an image. Now, typically the images we have are color images. Now, color images are represented as 3 different channels. Typically red, green, blue, but it could be there are like other ways to store colorful images. Now, it is not treated as a 3D data, and this is something which I've seen a lot of people get confused with, right? Because they'll think, oh, if my image looks like this, this by design looks like a 3D, because 3D data means that you have 3-way connection about data. But in this case, the data is actually only 2D because each of the channel, they don't talk to each other, right? That is basically 3 set of 2D images just put side by side, right? Each of them kind of represents idea for the same XY location, but there's no interaction going on between red and the green and the blue. They are supposed to be like almost basis values there, in the sense, whatever value of the red at a certain pixel, that doesn't tell you about what the value would be about the blue or the green, and they're supposed to be independent. So we'll see why, because there are some data where it is really 3D, right? If you have a cloud point data, or if you actually have RGBD, where you have these cameras that take depth information. So there are 3D data, like for example, MRI, CT, ultrasound. These are 3D data, and therefore you will use 3D convolutions on those. But on images which have multiple channels, you will still use 2D convolutions, except you will treat each of the channels separately, do them separately, right? So if I had a filter for, my filter is a size 5x5 for my, 2D image 30x32. If I have 3 channels, I'll just have 3 separate filters. Now, these 3 separate filters could, could mean the same thing, but they don't have to. They are just together. We just put them in one variable, but ideally they could be learning completely different things. But just that we call them, oh, this is one filter for this image, but there is actually 3 separate filters because we treat all these 3 channels separately. And again, this is something like I'm teaching you very basic. This is how it all started. If you read some of the latest, techniques, innovations, people have figured out that maybe you could, share the filter across the channels. That way you save more parameters. And then idea is, if you have parameters saved here, you can use it later on to have more depth, and all those things have come about. But the basics of it, the fundamentals of it is that each filter has its own, so each channel has its own filter, and you don't interact with them, you don't mingle them. Okay, so now let's see how, what an output of this would look like, right? So we'll do this one at a time. There's one channel at a time. So even though we have 3 inputs, we have 3 filters, let's take the first channel and let's take the first filter, do the convolution. Input size is 32, filter size is 5x5. Okay, let me see if you guys understood the calculation for the output size. What would be the size of the output if I'm doing a valid convolution? That is no padding. If I'm only going to do convolution, if I can fit the exact amount of data to the filter.
1.
1? No, so I'm asking what will be the output size, right? So here is 32 by 32 by 3. It'll definitely be 3 because each channel will have the output. What will be, we definitely know that it won't be all 32, right? Why? Because when the filter reaches towards the end, there won't be enough.
Oh, I thought you just asked if the filter matched the dimensions. You're asking about the one on the screen?
Yeah, yeah. I'm asking the one on the screen where, you know, what would be the output size after doing this convolution. So we know that
30,
when we had a
30 by 30.
30 by 30, right? So so you have 5 by 5, right? So okay, let's do this, right? You know, I think it's important to.
Yeah, I mean, I know it'll be smaller, but I don't know why it's 30 by 30 versus 31 by 31 versus 28 by 28.
Okay, let's find. Okay, let's do this, right?
I mean, I could draw it out, but is there a formula?
But I mean, there is a formula, but I want us to be able to, like, let's derive the formula, right? So the in that, even if you forget the formula, you'll be able to, you know, make it a 1, 2, 3, 4, 5. So when you have 5 rows, you know, so 5 columns, and you know you have a fill, you have a kernel of size 5, you can do this because, you know, input matches, right? So, you know, we are convolving for this one, and there will be an output, right? Because, you know, when we are convolving for this pixel, you know, my filter would basically go from here to here, right? And therefore now when I'm convolving for this filter, sorry, this pixel, you know, my kernel exactly matches the output. Now, if I want to go to this pixel, as you can see here, I can definitely have the, you know, 2 on this side, right? This is a third one. I need 1 more here, right? But that doesn't exist. It means I can't do for this row, and similarly, I can't do for this row, right? So the output will be less by 2 pixels on, you know, on one axis, similarly less by 2 pixels on the other axis, right? Do you think now you can be, so say if it was 7, right?
Yeah, I guess my question is, why can't you just do the computations anyways, right? Because the x will have a value of 0 in that case, because the x doesn't exist. So why can't you still just do the multiplication?
That's a very good point, and I'm glad you asked that, because, and there's a very important reason why you would not anyways do the computation. Okay, let's go back to that window, right? So here, imagine, you know, so here, look at all the values in the gray, right? Oops, come on. I wish there's a way for me to get out of this without having to move the pixel. So here, like, so look at the values in the gray here when I move the pixel there, right? So when you see here, you know, and say my kernel is something like, okay, something like this, right? So there is some value in, so there is some value in all kernel values, right? And you can see here now, you know, the total sum is like what, 134, right? And imagine if I didn't have the last row to sum at all. All of the pixels, you can see here, all the pixel values, you can see the output range is going from what, like 100 to, you know, like 134. But if I don't have one of the rows, its magnitude will be completely off compared to everything else, right? And that look very different. And therefore that is, you know, not part of your image, because your goal is you're taking an image and you're converting it to be something else, but still you want it, but this is still an image, right?
What if there's important information on the edge of the image?
Yes, so I'll go, so that is a really good point, and that is always, and that is, you know, most of the time that is the case, right? Image kernel will have, and that is where the idea of padding comes in, and I'll come to that padding. That is, you imagine that there are, you know, a few other, that there are boundary pixels, and those are just 0, and then you do the convolution. And typically, and if you do padding, then, you know, your output size is always same as the input size. And we'll come to the padding. So yes, there is a way to do it, but either you add the padding, right? And then you add the padding in such a way that, you know, so for example, if your kernel is 5, you add 2 padding layers. And if your kernel is 7, you add 3 padding layers. And if your kernel is 6, you still add 3, because basically this is, you divide this by 2 and you just take the, what is that function called? The quotient, right? That is 5, just so you take the quotient by dividing it 2, because, the odd one doesn't matter. Now, somebody had a question, do we always use odd? Almost always I've seen, people use odd. Why? Because, then there's the idea that you're doing for a central pixel, but it is getting impacted by all its neighbors. If you do even, then it's not clear which pixel that you are trying to convolve. There are some special cases where, in some special scenario where you might want to use even because there's some prior around it. But if it is just images and you don't know anything about the images, you should always use odd, because then when you use the odd, the center of the kernel is the pixel for which you are trying to use the neighboring information. But if you have 4 by 4, then it's not clear what is that pixel which is corresponding to this computation. Go ahead, you had a question.
Yes, when we looked at 32 by 32 and we came to this new shape of 30 by 30 after applying the filter, but I think it should be 28 by 28, because if we try to move with the filter to the top left corner, and then we apply it to the center of this filter, so we are chopping off 2 on one end.
Absolutely.
Then we move to the right corner, we're chopping off 2 on the other end.
Exactly.
So that is 28 by 28, right?
100%. And I was intentionally doing this only on one side because I wanted to show you that even when you start the convolution process here, you cannot do the first column and the second column, right? You still have to go to the third column. And similarly, you cannot do the last row and the second last row. So you reduce it by 2 from this side and also from the other side. So you're 100% correct. And I think I have the output written in the next slide, that it will be 28 by 28 if you do the valid convolution. Yeah. I'm glad you caught that. Okay. So, and you can see here, this is what the output size is, right? 200, because from this side also you don't do the first 2. So, so you simply divide the kernel by 2 and take the quotient, and you see how many pixels you have to remove. Okay. And then of course, if you can, we'll come to the padding, but in this case, because we had, 3 channels, you'll have 3 outputs, right? Now, there is, so this is one filter, right? And you can definitely have, more than one, so you can have multiple filters, right? And then you'll have multiple. So the number of input, the number of channels in the input depends on your data. Typically it is 3 or 1. Number of output depends, because if I learn 2 filters for each, so 2 kernels for each filter, you can imagine, you can see how there is like 3 varieties of each kernel, because 1 for red, green, blue, and therefore the number of outputs and output channel will be 6. And this is where you'll see when in most of the networks, this in fact goes all the way to like 128 or 64, because at that point it is no longer image, right? Because if you're still thinking, oh, somehow this all of this should combine together, should look like an image. I mean, it started like that. Like started with the idea that yes, you do a convolution, you have an image that has some properties or something has been extracted out. But with deep nets, we do, our output is not an image. We'll come, I think next week we'll be learning like genetic models where it is where output is an image. But for now, for these purposes, our output is much lower dimension. Typically, it's a classification. So we don't really need to preserve the structure of the image. So you will see here how with each layer, this whole piece of data will start to look less and less like images. And I'll show you what it actually looks like, but it will not look like a normal image that you are used to seeing. Okay, so this is this is a convolution layer, right? So so last time when we learned about a dense layer, that is, there is an input, there is a certain number of neurons, every input is multiplied to every neuron, and there's an output size, right? That is the size of the neuron. In convolution layer, you have the input, you have the number of filters, And then there's output, and the output is determined by the size of the input spatial, and the depth is determined by number of channels and number of kernels. Okay, now what is a convolution neural network? It's basically applying the convolution layer, then applying a ReLU. ReLU is our activation, and then doing this a couple of times, in fact several times, and this is your template for a convolution neural network. This is what it is when people say convolution neural network. Now, how many filters will you learn? How many layers there will be? Now imagine if, let's say, you're only doing valid convolution, then you can see here you are going to be limited, because with each input you are going, with each convolution you are reducing the spatial size. So you can only go so far in the depth, and especially if you have a convolution with a stride, the whole output will be even halved. So the number of layers will be reduced by that, and that is why also people started doing padding, because now that preserves the spatial size, so you can have any number of layers as you want. Okay, so yeah, so this idea of the padding. So padding is you assume that you have zeros at the start and at the end, and now you do the convolution, because in this case filter size was 2, you only need 1. Similarly, you can do with your 2D images. Here you can imagine there's outer layer. Now question is, should the value always be 0? Because if you imagine, the example which I give you here, the whole reason I was telling you that it is a bad idea not to do convolution, not to do convolution where only using 2 rows, is because the magnitude of this will be very different. But it's still going to be different if you assume 0. So oftentimes people will, in padding, instead of using 0, you will use what is called as a reflection padding or a mirror padding. That is, you assume the final layer. So for example, if it is 1 layer that you have to add, you assume it's the same as the last layer. Assume there's like a mirror here, and then if you have to add like 10 layers, like 10 columns, you go to the you go to the 10th last column. So this is a mirror. Sometimes you do a reflection. So reflection or mirror. So these are the type of the padding people use. But again, those things are more meaningful if you are trying to get an output that has image-like properties, because you are trying to maintain the distribution of the neighboring pixels. But if you're just trying to reduce the dimensionality of this because you're trying to do classification, it turns out it doesn't matter, and doing 0 is good enough. Because even if these numbers are different, the model learns to adjust the bias, learns to adjust the weights to make use of it. And more importantly, for most of the images, in this image, if I don't do the convolution for the last 2 pixels here and there, it is not going to matter a lot, right? The image hardly changes its meaning if I remove certain pixels. So that's also something that happens. Okay, where we were. Okay, so so in padding, this is what it looks like. So now you have filter size 2. Now in this case, you can see the stride is, if you do a stride of 2, a padding of 1, you get output like this. And by the way, this GIF comes from a nice GitHub library where you can give any input size, any kernel size, any stride size, and make the GIF for you. So I'll encourage you to use that if you're confused what output will look like. And same thing, now because our input is like this, height, width column, the output will have it in the number of channels, number of third dimension now equal to filters. This will be equal to width, this will be equal to height. Now it is true that, okay, now question is, like I said, in classification, we want to reduce the dimensionality. That is, we want to go from height, width column all the way down to like 10 numbers. So oftentimes, doing convolution is not enough of a reduction. So we do this step which really reduces the amount of data, and this is called as pooling, right? So in pooling, the idea is you basically group the data. So in here, so say if I have a 2D image like this, and if I'm doing a pooling with 2 by 2, and similar as kernel, it has a 2D filter size. So I'll take a 2 by 2 size box, and all of this box reduced to a single number, right? And again, this is also often done with odd numbers, but here I'm just showing you an even number. Now this, all of this 4, now it could be what, averaged out, right? So, or it could be max, you just take a max value. And then, now in this case, if I had a stride of 1, I will be doing 1, 4, 2, 5, but because I have a stride of 2, I'm doing 4, 9, 5, 8. So you can see this, 4 by 4, which is 16 values, has already been reduced to 4. Right? It is a huge reduction in the amount of data, because our goal is to reduce these high dimensional images into a much smaller dimensional representation where you just know what the object is. Now, similarly, you are doing, so you say you have this size 2 to 4 by 2 by 64. Now, pooling is almost always done spatially, right? That is, you will never pool the filters, because each of this filters, each of the thickness, you should be treating them as like completely independent data, right? Each of the red, green, blue is like all independent. So all these processes are done on XY space, not on Z space. And again, in this field, every rule has an exception. You'll see people have figured out that you could also do this and that, but the foundations are based on doing them X and Y. Now, the reason we do this is, think of this right here. If this is the image, if I've extracted some edges, probably I could, now throw away some of the points, because edges are inherently, they will still be good on a lower dimensional representation of this image, right? Therefore, you could reduce the size. Now, here, this is where like one of the most confounding thing comes to, like, why max? Why not average? Because it turns out you are just trying to find a feature, and as long as a feature is present, that has some maximal signal, you don't care about the rest. So basically, this box is like, oh, there's a whisker. So if there's a whisker or not, if this value is large enough, probably there's a whisker. I don't care about the orientation of the whisker or other information that it captures. And that is what, by doing max pooling, you basically are maximizing presence and absence of feature rather than quantifying how much of the feature is present. And if you're trying to do classification, cats versus dogs, that is what is needed. And you will see later on that almost always in convolutional neural networks, you'll use max pooling rather than average pooling. And now, this again from the guy who is known as a godfather of deep learning. This is what he says.
Hey, can we pause here?
Sure, go ahead.
You lost me a little while ago. So, I mean, like, I'm following your computations, but I don't know what they're doing. So is what you're calling a filter, is that equivalent to a layer, or is the activation map equivalent to a layer? Is the size of the filters, the neuron count? Like, I don't understand like how these relate. I get the computations you're doing, but I don't see how it fits in.
Perfect. I'm so glad. And guys, always feel free to pause me, because sometimes, like when I'm full screen, I don't see the messages. Here, I will show you exactly. Let's try to do this, right? So I said this is what a convolution layer is, right? There's an input, and then you get an output. So convolution layer. So when we talk about convolution layer, we talk about this process of converting an input and then getting some output, right?
Okay, so a convolutional neural network is a network that includes transformational layers.
Right, exactly. So typically,
so the convolution is just a transformation.
Exactly, convolution is just a transformation. But when you have a transformation with multiple kernels, that all of them together is called as convolution layer. So if you had, so we talked about one process of convolution, right? That is, we say this is again too many.
But does each one of those output activation maps on that other slide that you just showed, does each one of those go into the next layer or the next neuron? Like, do they all go into the same neuron of the next layer, or do they get distributed to the next? That's where I'm having trouble piecing your slices of maps back to the initial image that we learned that's on whatever it was, slide 21 or.
Okay. So the goal of convolution layer is to take an input and then produce the output, right? Now, what happens to this output after this, that is not the concern for this layer, right? That is up to the designer. Like, say you are architecture designer, you will design what to do with all these 6 channels and 28 input. Now, it is, like 99.9% of the case, you will treat it as input to the next layer, and then you will have another convolution, right? So let's try to, so let's duplicate this, and let's say I want to add another convolution layer after this. So in this case, how many in this convolution layer? So there are a few things that you have to decide, right? And you can see here on the equation there are a few things that they don't even have a default value. So filters means how many filters you want to learn, and kernel size. What the like these things, there's no default value, you have to provide. So here, looking at the input, let's write down what these values were, right? So here we basically did a convolution layer with how many filters? 2 filters, right? So because in there's 3 channels, so you basically have learned this. So 2 filters, and my kernel size was 5 by 5. And then when I did this, I got this output. Now here, I want to add, let's say, another convolution layer, right? Remember, so convolution layer doesn't know and doesn't care about what the input size, like you don't need to know the input size, right? So here I can simply say conv2d, let's say I do 10 and I do 3,3. So tell me, what does the output of this this look like? Because I think if you are able to write that, probably you will be in a much better shape in saying what the whole thing looks like, right? You want to take an attempt on what the output of that would look like?
So where do the number of neurons come in?
Yeah, so the number, so neurons, so these are the neurons. This filter is what is the neuron, right? Because if you go back to this image, right? Sorry.
Well, because that says
Filter the weight. So you're thinking of these as the neurons, right? So now, because this is where little the whole connection between convolution layer and MLP a little bit goes out of, because in this case, we have this idea that these are the neurons, right? But remember, this picture is just a computation, right? In reality, there's nothing physical here. Even when we are doing MLP, the things that we store or that we have are the weights, right? And then you take the weights, you take the input, you do the weighted sum, and then you apply the nonlinear layer, max, ReLU or sigmoid, and that is your output of the neuron. Neuron in itself, doesn't exist in its own. The neuron is a place where these computations come together to happen, right? Similarly here,
okay.
Yeah. So where were we?
You're on like 20, 18, yeah, 18 and 19.
Okay, I thought I made another. Yeah, okay, this one, right? So here, we can treat all of this as that one. So basically, each of this one square block is like a neuron. So this 6, if I were to put them in a vertical row, that will start to resemble what we had before, right? But because they are like this, I'm putting them stacked side by side instead of putting them stacked top to bottom. But if I were to stack top to bottom, that is what is your neurons. But like the actual weights are the kernel filters. And if I were to do this now, basically I will have let me copy one of this. I thought all of this were separate images. I don't know why. Okay, I can complete this image later, but you can imagine now here a stack of like 60, right? Because 10 multiplied by 6. And remember, this number are also it's a matter of convention, right? Sometimes people, this could be 60, this could be 10, it depends on the implementation, right? But this 60 channels, and the output will be -2 here, sorry, -1 here, minus here, so 2 is gone, so 26. 26, right?
24.
24, right? Yeah, because 2 both sides, 24 by 24. So you'll have 6 by 24 by 24, and that will be your output of the second convolution layer. So yeah, go ahead. You have a question?
Yes. So I had a question regarding visual representation of. First, we looked at neurons as nodes, and now we're looking at them as like 3D images. if we imagine this 5 layers with dimensions of with like a subscript I, J, and K. So let's say I goes from 1 to 28, J goes from 1 to 28, and K goes from 1 to 6. And if we were, and since this in the middle, can I annotate?
Yes, sir, go ahead.
So this in the middle is like it's a layer, but if we were to draw in our representation, then each of them will be I, J, K. And can we do as many as 28 times 28 times 6? So if we were to represent in a 2D way, a 3D block of data, can we do that by ... and the last one will be with the subscript 2023. Can we do that?
Kind of, yes, you can do that, but I would say that even these 3 should be put separately, right? Because the way these things are designed is that, imagine that there's like 3 separate images, right? Like just somebody gave you 3 set of data and you are doing all this process, for all of these 3. So first of all, split this, 3 by 30 by 32 into like 3, so first let's flatten this 32 by 32 into one line, right? So that is 32 multiplied by 32. How much is that? Okay, let's,
almost 1,000.
Yeah, okay, right. So say you have this 1,000 neurons. So 1,000 inputs, right? Now, so I'm basically, oops. So you get the idea, right? So I will not do all 1,000. So let's say I have all these 1,000. Now, question is, here I'm putting in this in 1D. In reality, they are, in the computer represented with XY, but they are 1,000 different points. So I have these 1,000 points, and then I'm doing some convolution. So I'm doing a valid convolution. So I will now, instead of 1,000, I will have, few points less, right? So I will have, just a few points less, and it will look like this. Right, and now this is for one of the channel. Now you basically repeat this whole thing for green channel and then for blue channel, right? Now, question, remember, so just going from this to this is, it requires some filters, right? It requires some weights. So if it's possible to just change the color of this, it'll be so much easier. Okay, let's do this. This is green, this is red, and this is blue, right? So let's try to get as close to as well. Okay, so you basically had 3 different data, red, green, blue. So for each of the data, now this, remember, there is this lines, whatever we we're comfortable doing this, we have this weights, so we got this. So when you do this separately for 3 of them, you have learned one filter, right? Now this one filter has 3 different set of kernels, right? But this is called as one filter. And the reason this one filter has 3 different values is because we don't want these 3 kernels to interact. Now, this is where I said that some people have now started using the same. They're like, what, red, green, blue, whatever information is their model can, learn to mix them. But most of the implementation does not, right? So all these 6 different kernels is part of your one filter. Now, if you learn 2 filters, because in each layer, for MLP, we have to decide how many neurons we need to learn. Now you have to decide how many filters you want to learn. You'll always learn, so if you learn 2 filters, it means you need another 6 set of kernels, right? So you'll basically have another copy of this. Now remember, so this all thing actually runs in parallel, right? Because this set of computation does not need, this doesn't need anything from this set, right? And therefore, you can imagine all this 12 computation happening in parallel. And that is why these are all called as single layer, because they can all happen at the same time. So in deep learning, essentially the idea of a layer is when all these computations can run at the same time, because they don't depend on each other, they are considered as a layer, right? Because if I'm talking about layer n+1, I know I cannot do that until I've computed layer n. But any computation that happens in layer n+1 doesn't depend on the values of the same layer. So this is what it looks like. Even though here we are represented like this, this is what this thing looks like this. Now in this case we have learned 2 filters, similar, but here how many here we have learned 6 2 filters, so that's why we have like 6 different outputs, right? Now again, remember this number is sometimes hidden, because sometimes there's this idea that you will again average. So this is where sometimes what some implementations, what they will do is you learn these things, now you will actually add them together, right? Because the idea is all this red, green, blue is added together, and you will make one output. And now there's no longer okay, so let's give it a separate color. Okay, I'll change the color. I'll just change the color of I'll just so this whole thing is now one output. And similarly you have another let's see, and the output here. Now this is where it depends on the implementation, and people will basically sum this. Can I add a sum symbol here? Come on. So even though we used different kernels, the output is only one channel, right? So now if I'm learning 2 filters, I will only have 2, the number of channels will be 2, right? So here, if I say, if I said the neural network to learn 6 filters, the output is 6 channels. Why? Because red, green, blue, their kernels are convolved, then they're added, and therefore the output is 1. So now you have output of 6. Similarly, when you have, if you are learning 10, now your output will be 10. Why? Because this 6 will go, all of these 6 will be convolved and then be added to make one output. And then you'll do this 10 times, so you'll get 10 different outputs. Now, what is the difference between this 10 and the 6? There's no difference. It's only semantic distribution here. But this allows us to think of these things as a parameterized stuff, and you can scale them based on your needs. So is it now clear, like what does this convolution layer represent?
Yes, and you mentioned the second layer when we applied 10. Is it 10 layers?
Yeah. So so that the parameter name is called as filters, right? So here we will apply 10 filters. So when you apply 10 filters, so the reason I did this is because I don't want you to confuse it. This 10 doesn't mean like there are 10 kernels. Yeah, so the number of kernels will be 10 multiplied by 6. Why? Because each of these 6 will have a separate kernel, and then each kernel will be of size 5 by 5. So the number of parameters in this layer will be 10 multiplied by 5 multiplied by 5 multiplied by 6.
Okay. Thank you.
So far, so good?
Not exactly.
Okay, so what I'll encourage you is, first of all, look at that GitHub GitHub. And you can simply import this Python library in your notebook, and you can just call with many different inputs, and then first, like get the, good understanding of, the convolution process. And now, convolution. There is a nice tool. Where was that tool? This one. Because this also allows you to do this, but also allows you to do something like this. So here, what you can do is you can play with the parameters and see it happening in live. So say, let's start with very, so here you can see, right? So we have 8. So the input, what should be the input size, right? So how many? So you can play with this. Minus architecture. So this is a convolution layer. So we can add another convolution layer. We can give the values, right? And so, in that way, you can, you can see what the outputs would be. This is like the, okay, let's start with convolution layer.
Is the output, I mean, I know we're getting close to the end of time. So like, again, going back to my first question I asked, like, why? What's the point? Like, is the output a new image that has never existed before? Is the output a prediction, a classification? I think the answer is all the above, but.
Yeah, so you kind of, I guess, so probably will not be able to, so I'll break this into 2 lectures, but just to give you a hint on why, right? And, to be honest, it was first, like we saw the results, and then we started asking questions why, right? And it turns out, like the first layer, when you do the convolution, like we went to this kernel thing, the things that these kernels learn, they look a lot like edge detectors. In fact, they're slightly different types called as Gabor filters, if you're curious. So, and then the second layer builds on top of these simple edge detectors to basically capture some kind of motifs. So you can see here for organizing car, it is getting a sense of like what, like circle or a wheel. So this particular filter knows how, knows when a wheels exist. And remember, the filter is convolved all over the image, right? So as long as this filter can capture wheel, wherever the wheel is in this image, it'll basically get activated, right? And that's where the word activation comes in. Similarly, it is finding other patterns. And as you go higher and higher, it forms more and more, like it combines motifs to form more higher abstraction. And therefore it learns complicated ideas. In fact, it has so much understanding of the objects that if you see for barbell, it turns out like most of the images had a hand. It almost always thinks the hand is necessary part of the barbell, right? And we'll come to it in the future courses where I will show you some tools that allow you to introspect these kind of things. Like for example, there's this thing called as deep dream. I don't know if you guys have seen this deep dream, right? So the idea is what happens if you give an image and allow the computer to reinforce what it thinks that part of the image is, and it becomes very trippy thing. But you'll often see the it's mostly cats and dogs because the training example has a lot of cats. So whenever it sees some part that like has something closer to cat or dog, the activation of those signals are maximized. So to come back to a question why. Because doing this kind of a multi-layered convolution is able to capture semantics, the things that you would not be able to capture just by hand tuning the filters. Because if you hand tune filters, you can only capture these kind of very non-semantic, these are called as quantitative features, right? These are just distribution features of the image. Because like when I said sharpen, this sharpen doesn't really know that there is a phase here. Like everything is being sharpened without knowing the context. Whereas, if you use some of the new tools in Adobe Photoshop, when you say sharpen, it applies different kind of sharpening depending on what object it is. And that kind of a semantic understanding can only happen when, you train network, with like a lot of layers. And, for example, I will come to this later, but you'll see in the, like typical networks looks like this, like the VGGNet is like the used to be the most popular one. And you can see here how many convolution layers there is. And the idea is when you do so many convolution layer, you start to get this, very high semantic information, which we would not know how to capture. So I hope this answers why we do this. But to be honest, it was more like it first works, and then we started explaining why it works after looking at the thing we have built. Does that help, Tim?
Yeah, like I said, I'm just trying to relate this back to some of the stuff that I've
Yeah,
seen in
absolutely.
practice on my
100%.
team where we're using convolutional neural networks for regression problems on time series data. So I understand we're getting there. I'm just trying to piece together.
Yeah. So I mean, so question is, like convolution, just because it is regression doesn't mean it's not classification. Therefore, somebody's going to be using convolution. Go like if a convolution neural network looks like this, the first 10 layers or the first 80% of the layer is just basically filtering your information to extract all these semantic, or these qualitative ideas, right? And after that, either you can apply a classification or apply a regression. Like if you're doing where the object is in the image, you have to do some kind of regression, right? XY coordinates. So, you can do regression on top of convolution also. And in fact, it is done. But the first few layers is basically to capture. In fact, so for example, the way Google does the image search, right? Yeah, I'm sure you guys have tried using where you reverse search an image. And okay, no problem, Sanjar. Anyways, I will not continue much because there's a lot more left. I will have to split this into 2 lectures. And I'll post the video, but feel free to send any more questions if you have. But let me continue a few more minutes. So like for example, the Google reverse image search, what it does is it runs this kind of very, very deep network, and it stores this last layer values. So each of the images is essentially reduced to this vector, and typically this vector is called as embeddings, and so these are called as image embeddings. And now you can take these image embeddings and you cannot retrieve back the image, but you can use that image embedding as a proxy for an image, in a sense, proxy for what it contains. And therefore, now you can take this and do some regression on top of it, do SVM on top of it, and you can do a lot of stuff. In fact, most of the time, people will do that. People will take a very, very big network, extract the features, and then do a simple classification, or simple neural network, or simple machine learning model on top of these features. So this is called as embedding based training, or like using a pre-trained weights. And that is in fact, like especially in bio domain where there isn't a lot of data, that is the most common strategy for applying convolutional neural networks. So for example, if you guys are interested, I'll show you how to face. Actually, you can also do it in Keras. So you guys go to Keras, get. So let's see. So now, I mean, some of these names might not make sense to you. We will come to in probably in the next lecture. All of these are like very popular neural networks. So you can just tell what model you want to extract, and you can do like this. You can include top, means include the final classification layer, and you can just call this and give your own example, and it'll give you a vector, and therefore your image has been reduced down to that vector. Now you can do a lot of interesting stuff with that vector. And similarly, you can, and what about the kernels, the weights? They are all already saved by Keras. And in fact, it tells you how many kernel, how many parameters each of them has, what its accuracy is. I typically want to use a model that is really good. So let's see, these are the things we will study in the next week. These are like the currently like the best networks. And you can see even though they are much better, they aren't that they aren't that heavy in terms of parameters, right? Like this one has top accuracy of 90%, 143 million parameters. This has 93% accuracy and only 5.3 million parameters. So how you design the architecture oftentimes will win over the number of parameters. But of course, you can see the depth, 132 versus 16. So the time it takes to run some of these things could be much longer, right? So there are these kind of trade-offs, but by doing this kind of embedding extraction, you can reduce the image to a simple vector. Okay, so what we'll do is we'll stop here because I think there's already too much and there is a lot more to be done. What I'll do is on Canvas, I will post like a small to-do exercise where you can actually build your, like your own very mini convolutional neural network and try to just play with, like image data to see, you get a gist of, handling 2D convolutions and, what the parameters are, because oftentimes that is where the errors will happen, like not understanding what output size will be, and then, being surprised by having a different output size. So we'll do that. And then, next week we'll see, how these things are put together to make a really big neural network and some real practical neural networks, what their performances are, and then how it is being used for object detection and localization. Okay. Any other questions before we stop? Okay, I will